fission reaction, you have a neutron, and you fire the neutron at a uranium nucleus. Okay? If the uranium absorbs the neutron, it will become more unstable. It's already radioactive anyway, but it will become more unstable. And then what happens is the uranium will split into two new, generally barium and krypton, so two new smaller or daughter nuclei if you want. They still can be radioactive, so they still will be radioactive, the two nuclei that are produced. It will also produce 2 to 3, okay, separate neutrons. So just one neutron being fired at uranium will create at least 2 more neutrons with the other 2 nuclei as well. And it will produce some energy. Okay? The main thing in this reaction is the energy. The reason that there's energy created is because the mass before the reaction, or before the neutron is absorbed by the uranium, is not equal to the mass after. Okay? You have less mass on this side, so you have more mass with uranium and neutron, and when the reaction happens and you end up with barium and krypton, and 1, 2 or even 3 neutrons, you'll have some missing mass. Okay? The missing mass has to go somewhere. So this missing mass will turn into the energy, and then that energy that is created will be used to heat up the water that's in the reactor. The water heats up, produces steam. The steam turns a turbine, and then the turbine is connected to a generator, and so on. Okay? Now, what you can do, instead of having yourself to fire a single neutron at the uranium every single time, because every reaction produces at least 2, you can say in your exam 2 to 3, it's fine, but because it produces at least 2 separate neutrons, these neutrons can go on and they can cause fission in more uranium. Okay? Now, if you fire a neutron at uranium, it produces more neutrons, they go on and cause fission in more uranium, which produces more energy, and the process continues. This is a chain reaction. Okay? And a chain reaction is good, because what I want is, if I set off the first reaction, then I don't have to do anything else, because the neutrons that are created, they themselves will go on to more uranium, and will go on to more and more, and that reaction will continue, and energy is produced every single time. So I don't have to do anything. The reaction kind of sustains itself. So a chain reaction is good, but if you don't control it, for example, if you allow all 3 of those neutrons that were produced to cause fission in 3 more uranium, then each of those 3 will produce 3 themselves, and 3 will become 9, which will become 27, and then the energy will just spiral out of control. So a chain reaction is good. Okay? Chain reaction is good. But if it's not controlled, so unless it's controlled or not controlled, okay? If you allow the reaction to continue and you don't control it, then it will be an uncontrolled chain reaction, in which case you can cause explosions in the nuclear reactor, for example. It's the same principle as a nuclear bomb, yeah? That's how you would create a nuclear bomb. You set off the first one, and you would just let it go, you wouldn't stop it. In a reactor, it can cause an explosion, which has happened in 2 main reactors that we know of, yeah? So you have to control it. Now this is the process of fission, okay? How did we build a reactor to actually make sure this process happens, and then how did we build it and adapt it so that it could be controlled and different things like that? So these are the parts of the reactor that you have to be able to describe, you have to be able to talk about. You have the fuel rods, okay, which is basically just uranium-rich rods, okay? So you put the rods inside the reactor, we'll kind of draw a very simple diagram. You have the fuel rods if you want sitting there. Okay? So the uranium is what we use. You have control rods. Okay? Control rods. And the control rods specifically control the chain reaction. Like I said, if you don't control it, it runs away, it becomes out of control. Too much energy is produced and an explosion can happen. But it controls the chain reaction. The problem with this chain reaction is I don't always need 2 to 3 neutrons to go on and cause more fission. 1 to 1 to 1 sometimes is enough. So I have 2 excess neutrons or some excess neutrons, that I need to get rid of. Okay? So all the control rods do is absorb excess neutrons. Yeah? So control rods absorb the neutrons that you don't want to continue causing fission. Then we have a moderator. Okay? Moderator can sometimes be a solid. Some reactors, the moderator will be a liquid as well. Okay? So in exam questions that we've seen already, some people were confused because it gave you graphite and it gave you another substance, and people didn't know which one was the control, which one was the moderator. But it did say that one absorbs and one slows down. Okay? So you just basically call what it tells you that it's doing. Moderator slows down neutrons. Okay? Now, in this reaction, the excess neutrons that could go on to cause more fission are a problem. It's an uncontrollable chain reaction. I need to absorb them and get rid of them completely. Okay? But then, the neutrons that are produced by this that I actually want to go on and cause more fission, they are going to be produced very, very fast. Okay? And actually, if you just leave them, and when they're created, they're moving very fast, they'll probably actually not hit the next uranium that you need it to do. Okay? You want it to go on and cause fission in the next uranium. Maybe not this one. Maybe I don't want those two. I'll absorb those with my control rods. But this one, I do want it to go and hit another uranium so that it splits it, produces energy, and it can heat my water, heat my coolant. Yeah? Because they're so fast, if I don't slow it down, they may just leave the reactor. And actually my chain reaction will stop. Okay? So a moderator slows down neutrons, and the reason is to increase the chance of further fission. Okay? And then if it were a 3-mark question in the exam, the last one would be to maintain the chain reaction. Okay, that's the moderator. We have coolant. Okay, the coolant is the liquid that is heated by the energy. Okay, so the energy that's produced in every fission reaction heats up this coolant, which is a liquid. When it's heated by the energy, it produces steam. And we know that steam goes on to turn the turbine, and we know that the turbine is connected to the generator, which produces electricity. Yeah? All good? There is a little section, if you look in the textbook, this is a very poor image, but if you do look in the textbook, there's a little bit with a heat pump, a water pump, and a heat exchanger. Because what you want is the coolant that's obviously going to be produce steam. It's going to be passed through the heat exchanger to the turbine. But you need, obviously, the steam that you created to turn the turbine to go back in. Alright? You don't want to have to keep filling up your coolant every time it evaporates, turns to steam. Alright? So you have a heat exchanger which cools it back down, condenses the steam, goes back into the